Good evening, all. Myself, Professor Sangeeta Gupta from CBIT Hyderabad. Today, I wanted to share my knowledge with respect to computer organization and architecture. So, this course is introduced for the BTech second year students, and it is also used as a main source for various competitive exams like GATE and other competitive exams like NET, SET, and various other faculty related exams. So today I'll be speaking about the von Neumann architecture. Von Neumann architecture is as shown in the figure here, where we have a main memory. This memory is used to store both the data as well as programs. Then we have a central processing unit which actually does the entire processing, and it is responsible for executing the instructions, and hence it is composed of a control unit, set of registers, and also an arithmetic and logical unit. The control unit is responsible to generate the necessary control and timing signals. Registers are used to store data which can be easily accessed at a faster rate. ALU performs the required arithmetic and logical operations. Then we also have the input output devices that perform the required task by communicating with the input and output devices such as keyboard, mouse, monitor, etc. When we try to understand this von Neumann architecture with an example, we can see a small piece of code here written in C programming language. This code is used to perform addition of two operands. The data elements A and B are basically referred to as operands, and the result is stored in another operand or variable C. So when this program is compiled for both the data and well as program, entire program, and for the data, same set of machine code is generated. There is no differentiation to understand where exactly is program ending and where are the pieces of data. So this is the difficulty associated with von Neumann architecture. The main memory, it consists of both programs and data. Hence, whenever we are trying to access the data and programs, the bus used, which is a group of wires, is a common one. Common bus, it allows the access to data as well as programs. Now you might be wondering what exactly is data. It is a part of program itself. You can see that this void main int a is equal to 8, b 5c, and c is equal to b plus a. All together, all the set of instructions constitute a program. And whatever items we supply to these variables, like assigning 8 to a, assigning 5 to b, these are known as the data elements. So the data elements keep on changing. With multiple executions, we give multiple pieces of data, but the program will not change frequently. Hence, to differentiate data and programs, we do not have any feasibility in von Neumann architecture. It also supplies a concept known as stored program concept. So, as we have already discussed, the control unit generates the necessary control and timing signals. In addition to that, it also supports various operations, fetching the instruction from memory, decoding the instruction, and then executing the required instruction. It also supports pipelining and parallel execution of instructions. Pipelining is a process where the output of one instruction is given as an input to the another, and memory access can also be eased out with the help of this kind of processing. Registers are very fast in accessing data from rather than accessing data from memory. We have a wide set of registers. They are generally categorized into general purpose registers and special purpose registers. Accumulator is an example of a general purpose register, and the other registers like program counter, instruction register, stack register, flag register are all the examples of special purpose registers. So this was about the von Neumann architecture. So we need a mechanism which helps us to differentiate in between programs and data. There comes another architecture which is a renowned one, that is an Harvard architecture. So in Harvard architecture, we can see that the role of a central processing unit and the input output devices stays the same. But the difference occurs in terms of the storage. So data is stored in one kind of memory and the programs are stored in another sort of memory, where RAM is preferred as a suitable place to store the data. So RAM is random access memory. It is a preferable place to store the data because data keeps on changing frequently, and RAM is a suitable place to store the data on a temporary basis, whereas program changes infrequently or randomly. Hence, ROM, that is read only memory, is a suitable place to store the programs. Now, when we are using separate memories to store the data and programs, and once this program is compiled, the code generated is also residing in the respective separate memories. Okay, the first code is residing in the that is related to the data part, residing in RAM, and the second part of the code is related to the program part residing in ROM. The functionalities of all the other units like control unit, registers, arithmetic and logical unit, and the IO devices remains the same. Now, let us discuss briefly the differences between von Neumann and Harvard architecture. The main difference that we have seen is in terms of memory, where in von Neumann architecture, both the data and programs are stored in the same memory, whereas in Harvard architecture, data and programs are stored in separate memories. When it comes to the type of memory, RAM is used to store both the data and programs or a set of code lines in your von Neumann architecture. Whereas in Harvard architecture, RAM is the memory used to store data and ROM is the memory used to store the code or program. When we try to talk about the buses, common buses are used to represent the address, data, and control lines in case of von Neumann architecture, represented by the unidirectional and bidirectional arrows. But when it comes to the Harvard architecture, separate buses for address and data are used across the data memory and program memory. When we talk about the execution time, the code is executed serially in von Neumann architecture because there is only one memory and the time taken to access data from memory will be increased. Also, the time taken to execute the code is also increasing. Whereas when it comes to Harvard architecture, the code can be executed in parallel from both by accessing the data across both RAM and ROM parallelly, and the time taken to transfer the data is approximately one cycle in von Neumann architecture, whereas in Harvard architecture, the data and code both can be transferred in one cycle. In von Neumann, either data or code can be transferred at once, whereas in Harvard architecture, both data and code can be transferred once. And when we talk about the control signals, less control signals are generated in von Neumann, whereas more number of control signals are generated in Harvard architecture. Space required is less in von Neumann, whereas space required is more in Harvard architecture. However, von Neumann architecture, due to the less number of hardware devices, hardware components, and less number of buses, the cost is less. Whereas due to more number of buses and more memory space, it is said to be costlier. Thank you.